that I listed in your assignments to think about before you came today, so I hope this looks vaguely familiar at least, only that it wasn't titled Example 2, but we'll get back to this in a second, but just generally, a rectangular storage space is to be created against a building using 84 feet of chain link fencing. The fence makes up 3 sides of the space, and the building's wall forms the 4th side, and our goal is to maximize the area that we enclose with this fence, and there's some other rules about the space can't be narrower than 4 feet, because it wouldn't really be useful for putting in whatever we need to put in. So there's a lot of rules, and there's a lot of descriptions and whatever. This is something that's, kind of geometric in nature. You could draw a picture of this, not sketching a parabola or anything like that, but just sketching a fence in a yard that's being enclosed. So there's a whole bunch of different problems that we're going to encounter related to optimization. You do have an iMath AS assignment that's not due until, let's see, a week from Monday. So homework number 12, I believe? No, 12 is the 3-question critical value. Number 13, lucky number 13 is all of our optimization questions. It's longer, and I'll give you more details about that next week. There's some that involve some trigonometry, some that do not. We are going to do a rehash of some trigonometry relationships to make sure we've got that, either today at the end of class or Wednesday at the start, but I'll give you some pointers on where to look if it's not today. In any case, though, the whole premise of this optimization is that we get to use the relationships that we talked about between, if we can construct a function, we can locate things like maximums and minimums, or steepest parts or flattest parts, things like that that are some form of most or best, or least, I guess would be the case if we're trying to deal with maybe costs or something. But if I have a function that describes some quantity, I want to know when is that quantity at its highest. General algebra doesn't really help us so much. If I want to know how do I make this quantity equal 14, that's when algebra comes in handy. If I want to know how do I make this quantity as large as possible, this is when we get to use calculus skills. I mean, obviously you can use graphing calculators, etc., to figure these things out, or at least maybe get an idea. But generally speaking, as I kind of mentioned last time, that once you actually have an equation that relates some changing quantities in here to one another, where the dependent quantity is the thing that you're trying to find a maximum of, the calculus of it is generally not that challenging. It's probably a lot less difficult than setting up the relationship in the first place. But our calculus relationships that say, like, oh, when I'm at a maximum, my first derivative is going to equal 0 at those sorts of points. Or it might be undefined if it's a funky sort of function with a corner point. Or if I'm at a minimum, same thing. A derivative would be equal to 0. And solving an equation equal to 0 is something that we can do. Equal to most isn't something that we know. So we'll use those derivatives instead. Or if it's something like, when is this function growing the fastest? That might be maximizing the function, the function that we wrote, maximizing its derivative, meaning finding when its second derivative is equal to 0 even. But in any case, let's go back a step and then I'll actually start this up. So just generally some strategies for thinking about these problems. They're kind of long-winded. They have to give you a lot of details about what the rules are for the situation, what are our constraints, our limitations that we have, like the 4 feet situation, or how is this set up, describing something maybe geometric, or maybe some just arrangement or relationship between 2 or more quantities. But just read through the problem, see what you can understand. There's millions of types of these. It's not like, oh, if I memorize these 4 problems, everything's going to be like one of those. No, it's not. There are some things that problems will have in common with one another, like they might involve geometry, or just reading certain words that might become familiar, but every problem is to some extent unique, which is why it's a problem and not just a rote thing to memorize. So make sure you understand what the problem is talking about, orient yourself to the problem. So what I suggest is make sure when you're reading through it, figure out what's going on, what's possibly having a variety of different values versus what has fixed values or known relationships about something's greater than something else. What's the overall goal? Am I trying to find the maximum profit? Am I trying to minimize the distance to a fence? So look for something about a most or a least sort of expression. to think about maximizing or minimizing. If there's something geometric where you can draw a sketch of it, or if it is something like a function that's given, like the 2a squared plus b squared, once you start getting something that seems like a quadratic function, maybe you could sketch that. But the problem we dealt with last time had 3 variables, the a and the b and the output of matching together 2a squared plus b squared. So that's not quite something that we want to graph. That's not really what we're used to. But think about what are the different things we could measure. If you remember back at the beginning of the year, think about some parameters or variables that we have. What are some changing quantities where we could have something perceivably take on a whole variety of different values and therefore alter the outcome of this dependent quantity whose value we're trying to find the maximum of? What is it that we're allowed to fuss around with or pick different values for that give us that output? Is there some sort of known relationship? Maybe it's not geometry. Maybe it's something about like distance, rate, and time. Or maybe it's something about sine is opposite over adjacent, or some sort of relationship between the pieces that are given to you that you know how they're supposed to be related. So look for different sorts of relationships between the sorts of information that's given. And I think I said this one earlier, but there may be some things that are fixed values, like the 4 feet. The 4 feet that was mentioned in that problem, that doesn't seem to be changing. Don't know quite how that's going to play into the problem right at the start, but there's something about 4 feet, and that 4 isn't going to change to something else. And then think about when I say which change together. If you remember last time we had this 2a squared plus b squared, and it seems like there's a whole bunch of different variables, but a and b weren't really independent of one another. If I alter a, b is going to change suddenly because a and b had to add to 25. So if I pick a number for A, I've automatically then by default picked a number for B as well. So make sure if you realize that if you have a couple of different quantities that are necessarily interrelated like that, you can write down that relationship, or you can, if you don't know how to write it down right off the bat, maybe come up with some examples of pairs that go together so you can generate a relationship that shows, oh, well, whatever I do, whenever I pick a number here, I just subtract from 25 to get the other one. Oh. So the other one is 25 minus the first. That sort of like writing it down a few times so you realize how you can generalize the process that you go through to relate things. So in these optimization problems, the goal is to maximize or minimize some sort of quantity. If I have a function whose dependent quantity is the thing I want to maximize, then finding where the derivative is 0 or undefined, or looking at those endpoints will tell me all like where the derivative is 0 or undefined. Those are my critical values of my first derivative. Or looking at endpoints. Endpoints of the domain, just like we talked about with the a and b, they had to be between 0 and 25. So we had those endpoints on this quadratic function otherwise that wouldn't otherwise be there, but endpoints on a quadratic function tend to be either the highest or lowest points around. They're going up the sides of a parabola or down, depending on the situation. But think about trying to maximize or minimize those quantities by looking at critical values and endpoints, and make sure that this, looking for your overall goal. What am I trying to do? Maximize, minimize, just see which one you've got. So that first derivative 0 with the second derivative negative, oh, that's the curve down flat spot, so I'm at a maximum. Identifying what you've found once you've found something of interest. But don't get so tangled up in, like I said, the calculus end of it. Once you get that far is usually the easy part. Once you've gotten the function written down that you're trying to maximize or minimize, the function whose dependent quantity is what you want the most of or the least of. Because we're writing this just from some basic function types. And so once we get that, it's like, oh, this is a heck of a lot easier than anything I had to do with derivatives on the mastery test. So it's all kind of downhill from there in terms of it's easy. But the writing it is the hard part. So don't get frustrated that it's taking a long time and you haven't even gotten to the calculus yet. That's normal. That's the hard part of this because you have to set these up from scratch. So here's our example. And again, the key to this is being able to write a function whose dependent quantity is the thing that we're trying to maximize or minimize. And in this case, this problem here, we're trying to maximize our storage area. So I would like to write some sort of function for area of my storage space. Because if I could write a formula for area of my storage space somehow related to all the information in this problem, then I could figure out where it's at a maximum, and then we've met our goal. So thinking about things like this, if you don't know where to start, if you have these sort of geometric descriptions especially, you just think, well, let's see, I've got a building and I've got a fence. Let me draw the fence in a different color. So I want to do a fence that's 3 sides. It's going to be a rectangle. Maybe it looks like this. Maybe it's like long and narrow one direction or the other, but just kind of drawing something general. If I wanted to find the area of this, how do you find an area of a rectangle? Length times width. So my goal, length times width, base times height, x times y, whatever you want to use. I'm just using length times width, just thinking, all right, my goal overall is going to be to maximize this area. Now, obviously, I can't take a derivative of this area function as it is and get anything useful. There's no numbers in it. It doesn't relate to the specifics of this problem. But somehow then, if I think about, well, I could make these lengths and widths, and I'll just label this as L and W, so we're talking about the same ones. I could make those lots of different lengths, right? So I could make L be 15, maybe. So if L was 15, then this side would also be 15. And how do I know what the width is if the length is 15? Just as a random example picked out for no reason in particular. How do I know, how does that help me figure out the width here? Or can I figure out the width from that? Well, we've got 84 feet of chain link fencing. If I'm trying to make this enclosure have as much area as possible, I might as well use all of the fence, right? As opposed to just leave some of it sitting there. So if this is 15, meaning this side's also 15, that's 30 feet so far. Sorry, I'm not writing down the units, but just feet. So it's 30 feet so far, meaning I've got 50 something feet left, right? 54 feet. And I could find the area then by doing 15 times 54. But there's no reason it had to be 15, I just made up a number, right? Well, what if I don't just make up a number? What if I just call it L? How do I write an expression for this other side if L feet of fence have been used for the side that's indicated, the side that there are 2 of? 84 minus 2L, right. So 84 minus the 2 sides that are, minus the 2 sides that are L feet long is going to be how much is left for the other side. So this was just, just 15, and then I know how I'd find the other sides and how I'd use that 84. Now, I didn't incorporate everything into this, but this tells me how the length and width are related, or just writing this over here. The width, as I have it labeled here, the width is the side that there's 1 of in this rectangle, is going to use the rest of the fence besides what's used for the 2 matching sides. Now, I didn't have to write this that way. I could have started with, think of a number for W and make that up, the side that there's 1 of. And then to find the length of what I should use for the other 2 sides, well, if I picked this number first, I'd subtract it from 84 and then divide by 2 to figure out what each of the other sides would be. That comes out to be the same as if I rearrange this solving for L. This could also be written as W minus 84 divided by 2. Or, let's see, simplifying that, 42 minus 1/2, let's see, wait. 1/2 W minus 42? Something like that? No, other way around. So you could, there's no reason that I had to start from L and work towards W. We could have worked the other way around. It's just a linear relationship between those 2. But this is not the thing that I'm trying to maximize or minimize. This is just some other restriction that I have. And the restriction is related to the fact that I've got 84 feet of fence. I don't have as much fence as I want. If I have an unlimited amount, then I essentially have up to the size of my property I might be more concerned about. I can make this area as large as I want. But since I only have 84 feet of fence, I'm restricted. And so something like this, where it's based on some sort of restriction, is often called a constraint. If you see that word, something about a constraint, it's about using like the rules of the problem, how one variable is related to another, or what a limitation on one of the variables is. And in this one, we also have some other constraints or some other rules to follow, which have to do with, A, it's fence. So I know that W and L aren't going to be negative. In fact, they probably even shouldn't be 0 because that wouldn't make any sense. And actually, we know that they can't even be like just slightly larger than 0. What's the other part up here? We've got something about has to be at least 4 feet in no dimension smaller than 4 feet. So W can't be less than 4, L can't be less than 4. So I could write those down separately, but if I know one of them, then I have a restriction on the other as well. So I'll just kind of write this generally as W and L both have to be greater than or equal to 4. But I wouldn't want to, and they can't be as large as I want, because if they get too big, then that'll cause the other one to be too small. But just kind of thinking of this generally, and we'll worry about more details of that later. But these both have to be greater than 4 for sure. If one gets too big, the other one's going to be less than 4. So there's upper limits also, but we'll watch that. In general, though, we've got this. Now, it's not written as a function, but unlike the original just formula for area equals length times width, this one I could say that this describes area as a function of side length, this L here. So this is a function whose dependent quantity, I'll just write it fancier, A of L is equal to, maybe I'll even multiply this out because it's easy enough, 84L minus 2L squared. And this is some weird delay here. So I've got area as a function of L, one of the side length that there are 2 of. And so this is a function whose dependent quantity is the quantity that we're trying to maximize. So if you notice, this is a quadratic function, just as simple calculus-wise to deal with as the one that we were talking about on Wednesday. Like, oh, this is parabola. This one's a downward-facing parabola, so it's going to have a highest point at the vertex, and it's going to have lowest points at wherever the endpoints may be. I just need to make sure that that vertex of the parabola, thinking if I were graphing L and area as a function of L, whatever this, well, it's going to go through 0 here. I have some endpoints that don't make any sense, but as long as this vertex fits all our needs for, it doesn't make either of our variables less than 4. And notice that W is not in this graph, by the way. It's just L and A, because that's how we got this to be a function of one variable. But if I know L, I can find W and double check, make sure I haven't picked any illegal values. But certainly, regardless of exactly where those endpoints might be, because I can't have negatives and zeros, and there's that thing with 4, the endpoints aren't going to be what we're interested in. They're going to be lower than wherever this vertex is. So using knowledge of mathematics and quadratic functions, you can eliminate some of the, like, how do I know this is a maximum and not a minimum? I know that because it's a quadratic function that opens down, because I've dealt with parabolas since algebra. So in terms of how do I find this vertex, you can even use the old algebra trick, negative b over 2a. Or, since calculus does the exact same thing and this isn't very difficult, I can say, oh, well, I need to find the critical value of this function a, and so a prime in terms of L would be 84 minus 4L. And there aren't any places where this is undefined. It is just a parabola. It doesn't have any corners, but it does have a spot where a prime is 0. Only one of them, and it's at that vertex. And I can solve for that just by nice, simple algebra. 84 minus 4L is 0. So solving this, I should get L equals 21, right? Subtract and divide sort of things. So we just need to check and make sure that this fits all of our requirements, that this doesn't cause anything to violate one of our constraints. If it did, we'd need to check our endpoints or other points. But looking at L equals 21, I can see if L is 21, then W is 84 minus twice that, 84 minus 42. So W would be 42. So neither of these is less than 4. Neither of them is negative. So we're all good. And so these two values for the length and the width should give us the maximum possible area. Now this question, the only question was what configuration of the storage space maximizes its area. It doesn't actually ask what is the maximum area, notice, but that would be an easy second question. The first question would mean that I'd want not this 15 and 54, but I want actually to use 21 for this side that's occurs twice, 21 and 21, and then this side is 42. These are all measurements in feet. This uses all 84 feet of our fence. None of the measurements are less than 4, and the area seems like it's going to be pretty big. According to this formula here, I know that this is a maximum of this area for any length, and if you did, fuss around and say, well, what if I solve for the other letter? You would have found that the vertex of a different quadratic function would have happened at W equals 42. And then you'd have to plug back in to figure out what the L is that goes with that to check. But the configuration we're talking about, what configuration? Sometimes the questions are what are the dimensions, or specifically what's the length, what's the width, or what's the east side and the north side, or however it might have been described in the problem. But lots of times they ask you for the parts that make the maximum value, and separately, what is that maximum, in this case, area? So the configuration we want is we want this 21 feet as the doubled side by 42. And then the area of that is 441, 882. So in any case, just finding area, length times width. Or you could even forget learning the width at all and just say, oh, it's L times 84 minus 2L. Although the 84 minus 2L is your width. In any case, this would be our maximum. You can try any other numbers you want. You're not going to get anything smaller than that. If you, just as a note, if you did want to investigate, like, where are these endpoints? How do I figure out, like, this 4 feet situation? Even though that's not really that's not going to be something that helps us find the answer here, because that would be along where minimums are instead of maximums. If you want to investigate that, the easiest way might be through just thinking about the diagram. What if I make the length as small as possible? What if I make this side 4? How long is the width going to be? And what if I do the opposite? What if I make the width as small as 4? What's going to be left for the length? And think about the areas that go with those, or what that then range of both length and width values is actually going to turn out to be. Not just greater than or equal to 4 simultaneously, but you'd have for each of them a range of values that they could take on. So if you want to do that, you can. But if you can see that, oh, those endpoints are not going to be related to what I'm looking for, a maximum, they're related to the minimum, you don't need to spend your time on that. But just as a technical exercise, you can always do it. I mean, sometimes geometrically speaking, it's easiest to maybe think back, instead of just looking at your quadratic function, look back at your diagram. See if looking at your diagram helps this to make more sense. All right, so let's take a look at a different problem. So this one you haven't seen yet, and I'll read it. I know it's a little bit small. A square-based, box-shaped shipping crate, just meaning like rectangular prism sort of regular box, no pyramid-shaped boxes or anything like that. It's designed to have a volume of 16 cubic feet, and then there's a lot of rules about the material. The material used to make the base costs twice as much per square foot as the material in the sides, and the material for the top costs half as much as the material in the sides. We want to know the dimensions of the crate that minimize the costs of materials. Notice that there's not actually any costs of materials listed, so we just have relative costs. So think about this for a second. Maybe think about something you could sketch out, and what sort of computations would help you find cost, even though you're not going to have a number for it, because we don't have any dollar signs in here, or any other currency. So again, our key to optimization is writing a function whose dependent variable is the quantity to be maximized or maximized or minimized. What is it we're trying to maximize or minimize here? Cost. So we don't really have any dollar signs, but if I wanted to calculate cost, what geometric quantity is this kind of related to? What is it based off of for this particular case? Yeah, surface area. So I've got costs per square foot, not as numbers, but just relative, like this costs more per square foot than that. So if I knew a number of square feet of stuff, cardboard or whatever it might be, does it say? Material. If I knew how many square feet of material I needed for this shipping crate, and I'd have a few different types. I've got the stuff for the base, the stuff for the top, and the stuff for the sides. If I can figure out the areas needed for each of those, so surface area of this box, or you could lay it out and just think about the total areas for each of those chunks of the total box's surface area, what it's related to. I could multiply them by their prices and add it up to get costs. So the only thing is we don't actually have a number for cost listed, so we could just use a parameter for that, something to represent whatever our costs are. I would only really need to make up one parameter because I've got 3 different costs, but they're all related, right? One's twice as much as another, and the other's half as much as that same. But overall, if I'm dealing with square-based shipping crates, let's see if I can draw anything that looks reasonably like a box. And not up here. Hold on a second. Pen is not cooperating. All right, so if I have something that is, I'm going to make it not square in one direction, just so we can tell the difference. So if I have something that's square-based, top and the bottom are both going to be squares. Or I've got, whatever this length is, that's the same. And then I've got a height that may or may not be the same. But I'm trying to find the dimensions for the crate that minimize the cost. So of the, let's see, we've got the costs are what we're trying to minimize. But just in general, we don't have numbers for the costs of things. But which is the most expensive, the base, the top, or the sides? Yeah, the base is the most expensive. And which is the least expensive? The top. So I'm just going to write them in descending order here. So I don't know the cost per square foot in dollars, but I could make up one parameter and use that for each of these. So let's see. So the top was the least expensive. Let's call its price per square foot. I'll call it maybe P. The top costs half as much as the sides do. And the base costs twice as much as the sides do. So in terms of, oops, that didn't look like dots. Our cost per square foot for these items would be just all multiples of the same, whatever, they're all related to one another. One's twice as much as the other. I picked it this way so we don't have any fractions like half in there. We just have whole numbers. But this fits our description. Now in terms of, let's see if I can draw this. In terms of pricing this out, just in terms of, I just wrote down some letters, L's for the base, and so it's a square, L by L, and H for the height, the distance to the other square base. If I wanted to know the total cost, or an expression for the total cost of the base, I know it costs, well, in terms of this, 4p dollars per square foot. How many square feet is it, or what would be an expression for the number of square feet for the base based on this picture? Yeah, L squared. And then so it's L squared, square feet, and then just, well, however many square feet that is, times the cost per square foot. See if you can do that maybe with the sides and the top, and then write a formula a function in terms of one variable, and it will include a parameter for the total cost of the shipping crate. Now it's going to involve two variables at first, but maybe you can figure out a way to get rid of one of those. So see if you can write an expression for the cost somehow or another, all of it, and then think about how I could use some other factoid in here that we have not yet used to help us out a little. All right, so how can we, this has mostly P parameter that we know we're going to be stuck with because we don't know what it is. And L, there's one stray H in there. How on earth are we ever going to be able to not have to have both L's and H's here? Are L and H related by anything? Like if I told you L was 2, then L is 2. Can H be anything I want it to be? Nope, because of the one number that there is in the problem, that's 16, right? The volume of this is supposed to be 16 cubic feet. So if this is 2 feet and 2 feet, then this is going to be, 2 by 2 by 4 makes 16. Or it doesn't have to be 2. It could be like lots of different things. Only a certain number of easy to pick numbers, like maybe this is 4, and this is 4, and then this is actually 1, making it not look like this, but be short and squat. That would probably cause a lot of cost for my base, but there's no reason it has to be whole numbers either, so you can't really go through and do a guess and check and find an answer. You might be able to locate what it's closer to, but our relationship here, L and H are not completely independent of one another. And if you had LW and H maybe to start with, you might realize, oh, it's a square, so length and width or something are both the same number. But volume is length times width times height, or in this case, with our letters we have so far, L squared times H. We have two L's with the square base. So if the volume is supposed to be 16, if I divide by L times L, I'm going to figure out what H has to be. Or just rearranging this with 16 as the fixed number for volume. So that would mean that instead of writing H here, I could write 16 over L squared. Now, that makes this kind of an awkward expression. Let's see. 2p times 4L times 16 over L squared. That can be simplified a bit. First of all, numbers. Let's see. 8 times 16 sounds like, what, 128? And there's a p, and there's one numerator L and two denominator L's. So I would call this 128p times 1 over L, just because I know I'm going to have to do something with it. But you could write it 128p over L, 128p times L to the negative 1. However, there's lots of different equivalent ways we can write this. But our overall idea is we want to write an expression for my total cost. Let me call this function C. And the way we're writing it is going to be a function of L. There will be the symbol P in it, but P isn't a variable. But we need 4P times L squared, and there'll be some simplifying we can do, for the cost of the base, this lovely expression, whatever form you want to put this in, 128p times 1 over L, or 128p L to the negative 1, for the cost of all 4 sides. The 4 was built in here, it just got absorbed by the rest of the coefficients. And the cost of the top is just p times L squared. And notice that each of these has a factor of p in it, which that's good. If you want to factor that out, make it look more, like regular, I've just got one symbol, then I've just got everything's multiplied by p. That's fine. There are a couple of like terms here, 4pl squared and 1pl squared. So even if you just wanted to simplify this a little bit without factoring out the p and just say it's, I've got 5pl squared, and then 128p, I'll write it L to the negative 1. Looks prettier maybe. But here's a function whose dependent variable is the quantity we're trying to, in this case, minimize. Not a parabola if I graphed cost against length because of this L to the negative 1. So maybe a slightly less familiar sort of shape. But I know that L has to be greater than 0. Shouldn't be 0 or we're never going to get a box. So we don't really have an end point at 0. We have, well, as you can maybe imagine from this 1 over L, there's an asymptote at L equals 0 anyway if I graph this. But something else is going to be going on. I have a vertical asymptote. I don't have a horizontal asymptote. I have a quadratic function mixed with a rational function. If you want to think about the Cartesian graph of that, I believe in the domain that's of interest, we have something that kind of goes like that. So we've got a vertical asymptote at 0. And then as L gets larger, this term gets to be larger than this one. But in any case, there will be a critical value in a domain section that makes sense. The domain of this function just in general would be anything except for L equals 0. But for this problem, reasonably speaking, we need L to be greater than 0. Because it can't be negative, shouldn't be 0, couldn't be 0 anyway with this configuration. Because if it was, we'd never get a volume of 16 cubic feet. So the derivative's a little bit messier this time. I mean, it's not hard to do, but the algebra of solving for when is that equal to 0, and again, the reason that we're concerned about when is the derivative equal to 0, because we want to know where that pause is. This function, from its vertical asymptote, decreases and then comes to a pause and then increases again later. So we want to know where does that pause happen, because I want to know when is that cost at a minimum. So algebra aside, at this point we've done most of the hard work to this, but just as a note, p, remember, is not a variable. So if I were to take the derivative of this, the next step in finishing up this problem, p is just like this 5 here, some constant that's multiplied onto the front of this variable, L. I'm taking the derivative of cost with respect to L, so I'd have 5p times 2L to the first, otherwise known as 10p times L. And then the second term, I've got L to the negative first power, so I didn't write plus because I know there's going to be minus. I'm going to have minus 128p, that's just part of this constant multiple coefficient here, and then times L to the negative 2. So it doesn't look particularly easy to solve, but I've got something that has power function terms to it. So generally speaking, factoring can help. We can certainly factor out a factor of p. That I want to know when this derivative equals 0. So if I have this, I can take out like constant numbers. I can take out the p. I've got, if you want to write this over L squared instead of times L to the negative 2, that might help algebra-wise. But I want to I'll leave this at this for right now. But think about how you would finish up this problem. That's going to be one of your things to do over this weekend. We won't have a number value for what's this minimum cost, but we can find the length and therefore also the height that caused that minimum cost to happen regardless, because the prices for the different sides are all relative to one another. So it'll be, we could write what the total cost is in terms of parameter P, but unless we knew that, we wouldn't be able to get a final minimum cost answer. But what are the dimensions that minimize the cost? I'll let you think about that over this weekend. But before we go for the weekend, long weekend, I want to give you a little trig brief review here. Maybe. There we go. So, scoot this down a little. All right. So, trigonometry, we've dealt, you know all the derivatives of sine, cosine, tangent, secant, arc, secant, you know, whatever. You've got like 12 different trig things that you know how to find derivatives of. We haven't actually used a lot of trigonometry in this class, though it might have been a little while, so just a brief refresher. First of all, when you're dealing with general trig functions, unless it's something where it specifically states that, and this is typical of triangles, something that you're working in degrees, just assume that the measurements are given in radians for the angle measures. Trig functions typically relate, standard trig functions, not inverse trig functions, typically relate a couple of measurements, how they change with respect to one another, and an angle. So there's two length measurements and an angle that are related. We can also incorporate lengths around a circle to that, and radian measurements, again, are based on, well, they're based on circles, and so you might have been presented what radians are in a variety of different ways, but just in terms of, here we go, a radian measure, what that is, 1 radian is the same length around the arc of a circle as whatever that circle's radius is. So 1 radian measure, arc length-wise, corresponds to 1 radius length. So if this circle has a radius of 1, as it seems to here, then if I take its radius and I were to, like, you know, match it up along to the edge of the circle, this is how big 1 radian is. So it goes partway through the first quadrant. If you remember measuring angles within circles, you start on the positive x-axis and go around counterclockwise. So I'm doing this backwards, I'm confusing myself. So going around counterclockwise through the quadrants in order, quadrant 1, 2, 3, 4. So this is our initial angle here. Let's see, let me do this way. So measuring, going around this way. So that black hash, if you can see that, is right where the first radius length ended. I'll stop here. So I've got, in the first quadrant, that's 1 radius length. And regardless of the size of my circle, the radius of my circle, the same would be true. I've got 1 radius length, and somewhere in the first quadrant, the second radius length would take us into the second quadrant. The third radius length takes us almost halfway around the circle. How many radius lengths take us exactly halfway around the circle? It's slightly more than 3, and it's a number that we have a symbol for. Pi, yeah. Pi radius lengths, or approximately 3.14 radius lengths measured around the arc of a circle of any size are going to take us halfway around the circle, or 2 pi will take us all the way around the circle. So we've got 3 radians, 4 radians measured, 5 radian lengths measured, or 5 radian measures. 6 is almost all the way around. And then, ooh, slow computer this morning. 6.28-ish is all the way around. Exactly 2 pi radius lengths fit around the circumference of the circle, going around the arc that the circle has. So what I mean by it doesn't really matter what size the circle is. Here, let me zoom out a little bit. This is true regardless of what size of circle I'm dealing with. Stop. I'm not doing it. All right, well, I'll just go with this then. So if I have, let's see. Can I click once and just go a little bit out? There we go. So 1 radius length on any of these circles goes to a similar spot around the circle. Let me get this to, there we go. So at one radius length around a circle of whatever size, we're at the same proportional piece of the circle we've passed through, if you want to think about an angle growing from 0 to 1 radian in size. So this central angle here that makes these arc lengths here, so the central angle that this ray forms at this point in time is 1 radian, because the arc that it makes is 1 radius length long, or 1 radius length around the circle corresponds to 1 radian angle measure. So lots of times when you're learning about trig, you just talk about radians, or like, oh, we always have pi over 4 radians, or pi over 3 radians, or something that's a multiple of pi. The reason is because those form a nice, like a quarter of a circle, or an eighth of a circle, or a 12th of a circle, or something like that. But we can talk, they don't have to involve the number pi in terms of how big is this angle. It doesn't have to be something in terms of pi to be measured in radians. It can be any sort of number. But just remember that if you do see an angle that is measured in radians, then that tells you specifically how many radius lengths along the edge of the circle you've traveled. Now, another thing in addition to this I want to point out is the trig functions and how those relate to circles. I'm going to scoot us into a different quadrant so it's slightly more interesting. But just quickly, because I know it's about time to go, if I can get this back to letting me scoot things. There we go. If I'm over here, if I'm talking about this angle here, I'm just going to draw out where this central circle is. And see, this is at 2.39 radians. If I wanted to talk about the sine value of 2.39, you can see that in these circles by just comparing the horizontal, or the, sorry, talk about sine, the vertical and the radius length that we're dealing with. So this outer circle has a radius of 6. I don't know if you can see that, but this is 6 units long. And a sine value compares how high I've gone vertically to that radius. So it's going to be something less than 1. And in this case, I can see it looks slightly more than 4. It's like 4 point, I don't know, let me say 4.2. So the sine of 2.39, I can read off of this circle by saying, oh, it's this ratio of 4.2 to 6, which that should be about, what? Well, we can reduce that, but in any case, 42 to 60, that seems like I should be able to divide that. 7 to 10. And if you check this in a calculator, the sine of 2.39 is about 0.7. But you can see those in circle graphs. So I'm going to give you some places in the book at chapter 2 to look over some trig things for refresher, because we're going to be doing some things next week that involve optimization where there's a trig setup, a triangle or circle sort of formulation and relationships within those. That we're going to use those to maximize and do some other things with. But I will see you next time. I'll post the homework in just a few minutes. Have a good long weekend.